All right, today we're going to cover section 7.2, which takes us back over some of the things we talked about in 7.1 and expands on it a little bit. A few of these things we actually talked about in 7.1. We talked about what the graph looked like, and now we're going to actually introduce the actual correct terminology for that. So what we're going to do is we're going to graph y equals 2 to the x and y equals 3 times 2 to the x on the same graph. Now, last time we actually did this in our calculators and looked at it there, and we looked at them on separate graphs and described what difference this 3 made in the graph. Well, we're going to talk about it again today, like I said, and use the correct terminology this time. So when we plug in, for y equals 2 to the x, that's going to give me 2 to the negative 2. Remember that we have to move it to the bottom of the fraction, so it's 1 over 2 squared, gave me 1/4. And I'm going to take the rest of this column out of the notes that we did the other day from 7.1. If you need to see that again, you can go back to the first set of notes from 7.1, and it's there. I believe it's the very first example. So when I plot those points, -2, 1/4, -1, 1/2, 0, 1, 1, 2, and 2, 4, here's what that graph looks like. But then what I've got to do is I've got to multiply all of these values by 3 to see what this graph of y equals 3 times 2 to the x looks like. So 1/4 times 3 is, that would be 3 over 4. Let's get that fixed here real quick. And 1/2 times 3 gives me 3 over 2. 1 times 3 is 3, 2 times 3 is 6, and 4 times 3 is 12. Now my graph isn't quite big enough to put all of those points, but we're going to put as many as we can. So if I go -2, 3/4, -1, 3/2, 0, 3, 1, 6, and then the 2, 12 is the one that I don't have room for. It'll be way up here somewhere. Okay, and notice when I did that, I ignored this middle column and just graphed this x with these y values. Okay, so now let's sketch that in. Okay. And the other day we talked about that when your a value changed, that your a was your y-intercept, and we said that it looked like your graph was a little bit steeper maybe. Okay, we know that when your b value changes, it gets steeper when it's bigger than 1. We know that when your b is between 0 and 1, it changes the direction. But when your a value changes from a 1 to a number larger or even smaller, it just changes your y-intercept. It makes it look like maybe it's stretched a little bit, but all it is it has moved your y-intercept. That's it. So here's what they call it. They say that when a is greater than 1, that the graph is stretched. And when your a is between 0 and 1, the graph is compressed. Okay, we talked about stretches and compressions earlier this year when we dealt with quadratic functions and square root functions and absolute value functions. Stretch means it's pulled taller faster, and compressed. It's kind of smushed from the top and flattened out a little bit. It's kind of what it does. So then, if we go down to this example, oh, and I almost forgot, what happens if your A value is negative? If A is negative, just like with our other functions earlier this year, that is going to reflect your graph across the x-axis. Okay, and we're going to see that in this next example. So in this next example, they want me to graph y equals negative 1/3 times 3 to the x. How does it compare to the parent function? Well, your parent function would be just this part. What we want to know is, what does this do to that graph? Okay? And we just talked about that your A value is going to be your y-intercept, so it's going to touch the y-axis at negative 1/3, but it's also going to flip the graph upside down. So what I want to show you here real quick is with your calculator. If we grab it here, and we type in y equals negative 1/3 times 3 to the x. I'm also at the same time going to type in just 3 to the x. But I want to make, well, you'll be able to see that one on mine in red. Okay, so the parent function will be in red. Your negative 1/3 times 3x will be in blue. Okay, so let's graph both of those. And I'll get the big graph for you to see. Okay, so there's my negative 1/3 times 3 to the x. And in just a second, here it comes, is the parent function itself, y equals 3 to the x. Okay, so when it's y equals 3 to the x, notice on the red one, your y-intercept is 1. But when you put that negative 1/3 out in front as your A value, it makes your y-intercept negative 1/3, and it flips your graph upside down. Okay, so I'm going to just copy these graphs on here. If you wanted to be more precise with it, you could look at your table and your, actual graph, negative 1/3 times 3 to the x, uses the x column and the blue y column. Your parent graph uses the x column and the red y column. So I can take and plot those points. Let's plot the parent graph first. That's going to be 0, 1, 1, 3, and 2, 9. It's going to be up here. I can scroll up just a little bit to get a couple of those other y values. So when x is negative 1, y is 0.3. When x is negative 2, y is 0.1. And so here is our parent graph. But then, the one that has the negative 1/3 in front, I plot negative 2, negative 0.37, which is really close to the x-axis, and then negative 1, negative 0.111, and then 0 is negative 1/3, 1 is negative 1, 2 is negative 3, and 3 is negative 9. Okay, and remember, these tables just come from plugging in x values and solving for y in the function. Okay, you've been doing that for years, so rather than take a whole lot of time to do it, we're looking at it in your calculator. Okay, so what I need you to remember is that when you have y equals negative 1/3 times 3 to the x, this negative 1/3, it makes your y-intercept negative 1/3. It flips your graph over. Flips it over the x-axis, and it is compressed because 1/3 is between 0 and 1. The negative just tells me it's flipped over. Other than that, I pretty much ignore it. So now for the got it question, how does the graph of y equals negative 0.5 times 5 to the x compare to the graph of the parent function? So once again, this is your parent function, and I want to know, what does the negative 0.5 do to it? Well, here's what we know. Makes your y-intercept equal to negative 0.5. It is flipped or reflected across the x-axis, and it is going to be compressed because 0.5 is between 0 and 1. So now, all of the translation shortcuts we learned earlier in the year still apply for exponential functions. Do you remember when we had y equals x plus 2 squared minus 4? Remember, if it was inside with the x, that went right or left, and we did the opposite. If it came after the function itself, or after the square, after absolute value, after a square root, after all of that, that told me up or down, and we did the same sign as that. Well, all of that still applies here. Okay, for this one, they don't ask me to graph these, they just ask how does it compare to the graph of the parent function. So in this case, our parent function would be y equals 2 to the x. And what they want to know is, what does this minus 4 in the parenthesis with the x do? Because it's in the parenthesis, that is going to be either a left or a right shift. Minus 4 makes you think left 4, but you have to do the opposite, so this one is going to be shifted right 4. And that's your answer. For part B, my parent function is going to be y equals 1/2 to the x. And they want to know, what do all those other numbers do to it? Well, the 20 is going to make the y-intercept equal to 20. Because that is bigger than 1, it is going to stretch the graph. And my 10 out here, because it comes after the x, it's not in parentheses with the x, it comes completely and totally afterward, that is going to shift it up 10. So now, I'm going to give you just a second to do the guided question. See if you can do that. And then I will give you the answers to those, and we will move on to the next part of the lesson. All right, so the guided question 2A. This plus 2 is going to make my graph shift left 2. For part B, this 5 makes the y-intercept equal to 5, and this graph is going to be stretched. This 5 right here is going to move it up 5. We could graph these on the graphing calculator if you wanted to see them real quick and easy. It's not a big deal to type it in. So now we're going to talk about E. Okay, when they say y equals E, or y, that's approximately y equals this decimal, 2.71828. Okay, if you grab your calculator and you go back to your calculation screen and you just type in E, let me find it. It's right above that LN button where it says e to the x. So if you do second and press that, and just do to the first power, press enter, there's the approximate decimal. It never ends there. It doesn't continue to repeat necessarily in the same pattern, but that's what e is equal to. And we're going to come back to this a little bit more when we get to logarithms, but these are called natural base exponential functions. So when you have e to the x, e is your natural base, x is your exponent. That's how you know it's an exponential function, but it has a natural base. So if you're going to take your calculator and evaluate e to the third, you're just going to press second ln, and that ln stands for natural log. We're going to get there in a day or so. So e to the third, press enter. And on a test, I will tell you what place to round it to. Let's round it to 4 places for now. So this is going to be 20.0855. Okay. The guided question wants to know, again, how can you use a graphing calculator to calculate e to the 8th? You can type it in just like we just did, or if you were asked for a lot of different values, you can go to your y equals screen, and let's clear out what's in there, and we'll type in y equals e to the x power, and then we're just going to look at the table. So when x is 1, let's try this again. I want my big screen here. You can see that when x is 1, y gives me this value. And now it's rounded a little bit so that it will fit in the columns. But remember, if you arrow over to that at the bottom of the screen, it will give you a much longer value. So if I wanted to know e to the 8th, I would just arrow all the way down. There's my e to the 8th. And again, if I go to 4 decimal places, I'm going to get 2,980.5 0.95, and that will round up to an 80. Okay. So you can get lots of information about e to a power quickly from your table. So now, last thing for the day, this is another type of interest. Remember, we talked about interest the other day, and we just had, y equals a times 1 plus r to the t. Well, this is a different type of interest. This is continuously compounded interest. And this is where they don't wait till the end of the year to calculate how much interest. You are rewarded in an ongoing basis, whether it be daily or, or by the minute, by the hour. It is continuously compounded. And so we're going to use this new formula that they give me in this box. Okay, there's our formula. And here they tell you that where they write A of T, that's the amount that you all have in your account at any given time. That's why it's A of T. The P, that is principal. That's the amount you started with. So that is your initial amount. And then you have your base E. R is your annual interest rate, and T is your time in years. So for this problem, it says, suppose you won a contest at the start of 5th grade that deposited $3,000 in an account that pays 5% annual interest compounded continuously. So here's what I know. I know that I started with $3,000. So the principal amount is $3,000. An annual interest rate of 5%. So my rate as a decimal is going to be 0.05. And they want to know how much will I have in my account when I enter high school 4 years later. So the amount of time is 4. And they want me to express the answer to the nearest dollar. So when I plug into my formula, the amount after 4 years is going to equal the principal times E to the 0.05 times 4. So here's what I would recommend you do. And I'm going to have to get that phone, so give me just a moment here. This one's Sabarati. Okay, great, thank you. What I would do is go ahead and take your calculator and multiply the 0.05 times 4 so that you've only got one value up there as your exponent. So 0.05 times 4 gives me 0.2. And then you can just type all of that in your calculator. So 3,000 times e to the 0.2 power, hit enter, and I will have, rounded to the nearest dollar amount, $3,664 at the end of 4 years. So now what I want to do here real quick, and your book doesn't ask you to do this, but I would like to compare this to the simple interest formula we used last week. Where I had A of T equals A times 1 plus R to the T. Okay, so the amount after 4 years using this method will be 3,000 times 1 plus 0.05 to the fourth power. Okay, so if I type that in on my calculator, this time I get $3,647 if I round it to the nearest whole dollar. Okay, so not that much difference, but enough.